In this video, I'll demonstrate how to compute a chi-square test of independence for a 2x2 table. I'll do it both by formula and using SPSS. First, let's do the formula. We start out with a frequency table. On the left-hand side, we have observed preferences among people who are vegetarians. Most of them are not. 334 are not vegetarian. And 61 are. Now the question that we're trying to answer for this hypothetical problem is whether vegetarians have a preference for voting for candidate Smith or candidate Jones. And you can see that there's some apparent tilt in the frequency count in terms of the number of people who prefer Jones who also happen to be vegetarian. That is to say, among the vegetarians, there seems to be a preference for Jones. Now the question is whether or not this is statistically significant. So we use the formula, and this version of the formula is provided in the textbook by Wolkowitz. And you have the frequency expected by chance, given by this formula, row total times column total divided by n. What we're going to do is we're going to take each row total. Let me start that over. So column total here, row total here. 185 times 334, and then divided by the grand total. And you can see that set of computations right here. That value is placed into this box for the expected preferences. The expected preferences reflect what we would expect to see by chance. So on the one hand, we have the observed frequency pattern, and we want to see if the observed frequency pattern violates the null hypothesis of what we'd expect to see if there is no preference among vegetarians for Smith or Jones. So we do this computation for the expecteds for every cell in the right-hand side. Scrolling down in my document, I've got the computations all completed, and you can see all of the values that we would expect to see by chance. Notice that the row totals and column totals still match up with the observed values. Now, in order to get your final answer, what you want to do is use the second half of the formula, right here, where the chi-square, this is the Greek letter chi, the chi-square value is given by the sum of the observed frequency minus the expected frequency squared, and then divided by the expected frequency. So for each one of these cells, what we're going to do is we're going to pair the observed frequency right here with the expected frequency, so 171 minus 156.43, square that value, and then divide it by the expected, which is 156.43. And you can see that set of computations pairing the observed and the expected, taking the difference, squaring it, and then dividing it by the expected, and you put it down here into the formula. Do that for each one of the cells, and it's a lot of computations for this particular problem. The numbers get quite large because of the large sample size. And you have to keep going across all four cells. When you get to the final answer, it comes out to be 16.529. And then what I've done is I've taken the formula provided by Robert Rosenthal to transform your chi-square into an effect size R. The 1 in parentheses tells us that we can only do this transformation if it is a single degree of freedom chi-square test, which this one is. any chi-square test of independence that has 2 columns and 2 rows yields a single degree of freedom test. You can refer to your textbook for a discussion of why that is. I won't cover that here. But for our purposes, know that this is a 1 degree of freedom chi-square test. So we convert that into effect size R, and if everything goes right, then we'll be able to compute the same answers for both of these in SPSS. So I'll open a blank SPSS page, and I'll walk you through how to do this from the beginning. The data view and the variable view are both empty, and I'm going to create my variables. Vegetarian, and let's just call it vote. And then I need to have another variable called count, and that's where I'm going to put my frequency count. I want to give these variables values, so I open the value label box. If you click on one of these cells, you see that the button becomes highlighted. Click on that, and now we can type in 0 equals, I'll just say no for non-vegetarian, and 1 equals yes for vegetarian. And then for the voter preference, let's say 0 equals Smith is the first one, so I'll put Smith here, and 1 equals Jones. Now with those set up, I can go back to variable view, or rather data view. I'm going to have 2 columns, 2 rows. So vegetarians, actually let me recode that. Let's start with 0 and then go to 1. And once I have it set up, what I like to do is toggle my value label so that I can actually see the words that I assign to the different numbers in the variable label. Now I can do my counts. Now Smith, among the non-vegetarians, had 171. Jones, among the non-vegetarians, had 163. These are the numbers of people who preferred to vote for that candidate. Among vegetarians, Smith had 14, Jones had 47. So now I have the data set up, but before I run it, what I have to do is I have to weight the data. So going over to the data view, or rather the data drop-down menu, go to weight cases, click weight cases by, then take your count variable, move it over, and click OK. It's not going to do anything at this point. It just tells you that it assigned those weights to those values. Next, go to descriptives and crosstabs, and in order to make it match the document that I had on the screen a minute ago, I'm going to put vegetarian in columns and vote in rows. Go to statistics, check the chi-square, and check phi and Kramer's V. The phi coefficient is the equivalent of the effect size. Click OK. And you can see the answer here, 16.529. Well, it's 16.528. I'm 1 off on the 3rd decimal point, and that's okay. A little bit of rounding error. I had 16.529. On top of that, we see the actual table of counts for the observed scores. If you have an error of data entry, you'll see it here. But the important thing is that our chi-square value matched the computations, and there's your p-value. Now you also get a few other things here. You get the continuity correction, likelihood ratio, and Fisher's exact test. If you have any cell within your data up here, if you have any cell that has 5 or fewer observations, then you should use the continuity correction. And that'll give you a different value. It's a little bit more conservative. The p-value will get a little bit larger. We don't see it here because the sample size is so large, it's driving this significance level really far down. So the difference here isn't that big. I mean, the magnitude of the treatment effect is not that big, but because we have a very large sample, it's making the p-value get small. So again, if you have any one of these cells, of Smith and Jones, vegetarian, yes or no. So these cells here, these 4 cells. If any of those are 5 or fewer, then you should use the continuity correction. We don't have that for this data set. So we're fine using the Pearson chi-square on top. Now the last thing is to see whether or not we have the same effect size. I calculated the effect size to be R equals 0.205. And you can see here the phi coefficient. That's Greek letter phi, which is really the equivalent. Greek letter phi kind of looks like that. Let me try again. Kind of like that. It's the equivalent of effect size R when you have a 2x2 table. So that'll give you the same effect size as I calculated using the formula. So just to recap with the calculations, we have chi-square equals 16.528 from SPSS, and phi equals 0.205. And we have the same values over here with 16.529 for chi-square and R equals 0.205. Thanks for watching. I hope you found that useful.